Hello everybody, I hope you're having a wonderful day. Um, just to remind us, what we talked about on Tuesday was we worked together on some homework for proofs, and we did direct proofs, and we did proof by contrapositive, where the idea being that we write the contrapositive and we prove that instead of the original because they are logically equivalent, so it gives us a proof of the original. Today what we're going to do is we're going to look at another proof technique, and that is proof by contradiction. So what is proof by contradiction? Sorry, I meant to hit down on the PowerPoint. The idea behind proof by contradiction is that, well, if we have a statement P, if we can show that the negation of P is false, then P must be true. So if we remember our logic, if P was true, not P was false, and if not P was false, not P was true. And so if we can prove that not P is false, we will have proven that P is true. So the outline of a proof by contradiction is that we assume the negation and we show that it has to be false. So we assume something that we hope will be false or we know will be false, and then we actually prove that by assuming that was true, it leads to something that cannot be true. Such as we assume something's true and we get 1 is equal to 0. We know that's not true. Or some other type of thing along those lines, something that we know is not true. So let's go ahead and look at an example of that. And what I have is, suppose that, or I want to show that there are no integer solutions to the equation 6x plus 15y is equal to 1. All right. Now, since we're working by proof by contradiction, we're going to assume the negation of there are no solutions. So that would be there are integer solutions, or there is at least one. There is an integer solution to 6x plus, make sure I write this down the same way, 15y plus is equal to 1. So I assume that there is an integer solution to 6x plus 15y is equal to 1. And what I want to do is show that this leads to a contradiction. So we assume here that x and y are integers then, so there is an integer solution. There exists an x and y such that 6x plus 15y is equal to 1. So we're going to assume that, okay, we have an x, so 6x, and we have a y, 15y, such that 6x plus 15y is equal to 1, where these are both integers. So that means that 6x plus 15y is equal to 1. Now, what I need to do here is to get a contradiction. I need to get something that's obviously false. So how would I get a contradiction here is, well, there's a couple ways. The first way that I would do is just notice that on this side, if I divide by 3, what I get is 2x plus 5y is equal to, and then this side I'd have to divide by 3 and I'd get 1/3. Now the reason why I'm doing that is because notice on this side, recall that we said x was an integer and y was an integer. So what we should get is 2 times x is an integer, 5 times y is an integer, so this whole thing should be an integer. But we've just said that this whole thing is 1/3, so that implies that 1/3 is an integer. However, is 1/3 an integer? Well, no. It is clearly not. It's not a positive, negative whole number or 0. So that is clearly not an integer, so hence we have a contradiction. So we found something that we knew was false. So what does that mean? Well, what it means is that if there were integer solutions to 6x plus 15y is equal to 1, then 1/3 would have to be an integer. But since 1/3 is not an integer, that means that there are not integer solutions to 6x plus 15y is equal to 1. Therefore, we have our original statement is true. So there are no integer solutions to 6x plus 15y is equal to 1. All right. Just as a note, another way we could do that is we could use our modular arithmetic that we've been using in class as well. And what we could say is something like, well, 1 is congruent to 6x plus 15y mod 3. But if we do that, we notice that we can substitute in what each of these are mod 3. 6 is congruent to 0 mod 3 because it's divisible by 3. 5 is congruent to 0 mod 3. So what I get here is 0 times x plus 0 times y. So 0 times an integer plus 0 times an integer mod 3 is just 0. So if we had used modular arithmetic, what we're claiming here is that 1 is congruent to 0 mod 3, or 1 is equal to 0. As I said before, that's clearly not true. Therefore, this is a contradiction. So again, we get that this must be false. So there must be no integer solutions to 6x plus 15y is equal to 1. Now, I wanted to go through this one because there's a few in the homework like it, and it kind of gives you an idea that, okay, well, I assume the negation. I proved that there must be something wrong. So therefore, my original statement was true. All right. The next thing I want to do is I want to work through a couple of the more well-known proofs by contradiction and some exciting results, and I'll explain those as we get there. But before we do the next one, I want to say, let's suppose I have an integer a and b, and if 2 divides a times b, then 2 divides a or 2 divides b. So now I'm going to need this one for my next proof. Sorry if you can hear the yard workers in the background. I would tell them to be quiet, but I don't think that's going to work. Alright, back to this one though. I do want to say that we're going to need this for the next one. So this one we're not going to prove by a contradiction. We're actually going to end up using a contrapositive here, because that's going to be the one that works out best. But we need this, so we're going to go ahead and prove it. Alright, so if 2 divides a times b, then 2 divides a or 2 divides b. We wanted to do that by contrapositive. So the negation of the then part is, the negation of an or is an and we negate each piece. So we get to assume 2 does not divide a, and 2 does not divide b. And we have to show 2 does not divide a times b. Alright, so that would be our contrapositive for this. And as I look at this, I want to think, okay, we're going back, we're doing this the same way we have been doing, so what is the definition of this? Well, if 2 does not divide a, that means that 2 is not divisible by a, so 2 is not even. Therefore, a is not divisible by 2. Therefore, a is not even. Therefore, a is odd. And so we can think about the ways that we've written that a is odd is, well, a is 2k plus 1 for some integer, or a is congruent to 1 mod 2. And so those were all equivalent statements. I'm going to continue to work with mods here. So I'm going to say, okay, a is congruent to 1 mod 2. And by the same reasoning, this means b is congruent to 1 mod 2. So if 2 does not divide a times b, what we have to show is that a times b is congruent to 1 mod 2. So here's our assumption, here's the definition that's equivalent, here's our then, and here's the definition that's equivalent. So we need to get from here to here. And again, we're going to do that by a substitution. I have a times b is congruent to. And now, because we're working mod 2, I know that I can substitute in what each one's equivalent to. So instead of a, I can substitute in 1. Instead of b, I can substitute in 1. So a times b must be congruent to 1 times 1 mod 2. Well, what does that mean? Well, 1 times 1 is just 1. So a times b is congruent to 1 mod 2. Therefore, a times b is odd. So 2 does not divide a times b. Now, just to recap that, what that's saying is that if a is odd and b is odd, then the product of two odds, an odd times an odd, is also odd. Therefore, the original statement was if 2 divides A times B, 2 divides A, or 2 divides B. So we're saying that if we find a product of numbers that is even, then one of the terms must have been even, because if I multiply two odds, I get out an odd. Alright, so that will come up. So using that, what I want to prove is that the square root of 2 is not a rational number. Now recall that I have up here a rational number is any number that can be written as a divided by b for some integers a and b with b non-zero. So what we're trying to do here is show that that's not possible for any a and b. So if I want to show that's not possible for any b and b directly, what I have to do is check every single integer with a divided by b, where b is non-zero, and I have to make sure that none of those squared are equal to 2. Now, the point here is that to check every single integer is impossible because there are infinitely many integers, and therefore to try to do a direct proof of this would be, well, you just couldn't do it that way. So you have to come up with some other proof technique to show that the square root of 2 is not rational. Hence, that is the power of using a proof by contradiction, is you'll notice that we'll actually get a proof out this way using a contradiction. But if we try to do it directly, there's just no way to do it. And that's why this is one of those proofs that they use to demonstrate contradiction, is because it is so clear that this is the best way to do it. That is, I can't do it by a direct proof, so I have to come up with something different. So I'm using my logical equivalencies to get this one out. Alright, so let's go ahead and go to the board and set this one up. If we're going to prove this by contradiction, we're going to assume that the square root of 2 is equal to a divided by b for some integers a and b, with b not equal to 0. Alright, so this is what we get to assume when we have to come to some type of contradiction. I'm not sure exactly how I'm going to do that, so I'm going to play around. But before getting into this formal proof, I want to talk about a over b. Last time I tried to do this later, but I just want to do this right now. If I take a divided by b, and let's suppose a is even and b is even, what can I do? Well, that means a is equal to, let's say, 2a1 over 2b1. So if both a and b are even, I can cancel out one of the 2's. Makes sense? Now what happens if both a1 and b1 are even is I can cancel out the 2's. And so I can get an a2 over b2, where a2 is less than a1 is less than a. And so if that's still even, I can cancel out the 2's again, and I can get an a3 over b3, where I've canceled out the 2's here, 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 and now I'm at this one, so I've canceled out a total of 3 2's, or divided both sides by 8, and I get a3 over b3, so a3 is less than a2, b3 is less than b2, and so I keep getting smaller integers, where these are all equivalent, because all I've done is cancel out 2's. Alright, so help me out here, guys. Do you think I'll be able to cancel 2's forever? Or will this have to stop at some point? How about a yes or no? Very good. So if I started at infinity, I could technically do it forever. However, what I do want to be careful of is they said a and b are both integers. Is infinity an integer? So now infinity would be the concept of let this get arbitrarily large. So I can say as it gets arbitrarily large, we have an infinite number. So we can have the concept of infinity within integers. But by saying this is an integer, that means that I fix this as a specific number. So I'm not going to let this get... So the idea is that if I wanted to express infinity, I would say let this get bigger and bigger and bigger. But because this is fixed, I can't let it get bigger, so this becomes a number. It could be a huge number, but it's still a number. So it is just an integer, so it can't actually be infinite. So it could be 10 billion or 10 to the 100,000 or however big a number you want, but it cannot be actually infinite. So if we started with any finite number here, which these will have to be finite, if I keep dividing by 2, that's not going to be possible to go on forever. So your intuition there is spot on. The idea is that if I'm able to divide by 2 forever, I would have had to start at infinity. But what I'm claiming here is that by claiming this is an integer, I'm claiming this is not infinity. So if I keep dividing by 2, I'm going to get smaller and smaller and smaller. So even this is 100 billion, and I can subtract 1, subtract 1, subtract 1, subtract 1. Eventually, I'm going to be at 1. And once I get to 1, I can't divide by 2 again because I'm no longer an integer because I'm 1/2 is not an integer. It's a fraction or a rational number. So the same thing down here. If this was an integer, I can't just divide by 2 indefinitely. Eventually, it's going to have to stop for one of these. The only number I actually can divide by 2 indefinitely is 0. So if the top was 0, I could keep dividing by 2 because I just keep getting out 0. But notice that b is non-zero. So because this is non-zero, I know, and it's not infinite, I will eventually have to stop dividing by 2 because otherwise I'll get some number that's no longer an integer. Do you guys buy that argument? If you don't believe me, you can... Okay. If you don't believe me, that's quite all right. I'm more than happy to go into more detail. And actually, I will be a little bit more specific in a future chapter about why finite non-empty set of integers always has to have a smallest number. And so we'll be a little bit more clear about that. But at least as an overview, I hope you guys can see I can't just divide by 2 forever. So eventually I'll be able to cancel out all the 2's that I can. So if I can't cancel out any more 2's, what that just means is that I end up with an A and B where A is odd or B is odd. It may still end up with one of them being even, but if one of them is odd, I'm done factoring the 2's. All the 2's are gone that I can get out. That has to happen eventually. So I may well as well may assume that when I wrote this, because these were each equivalent, I'm going to ignore the ones with all the ones that factor out 2, and I'm going to have to say that the square root of 2 is equal to an A over B, where either A is odd or B is odd. All right, so there's our premise. I have, okay, I'm assuming that it's rational, therefore it has to be A over B, where A and B are non-zero. But we just decided that we can factor out 2 so that either A is odd or B is odd. And so now what I want to do is I want to work with this. So I'm going to use some more room here. And what I get is the square root of 2 is equal to A divided by B. So if I square both sides, it's going to maintain the equality. So I'm going to get 2 is A over B squared. Therefore, 2 is A squared over B squared. So therefore, 2B squared is A squared. And so I'm just doing some algebraic manipulations. Why? Because I didn't know what else to do. So we tried that and we got here. And now I actually see something interesting. What do you notice about A squared? Somebody want to help me out? What property does A squared have? So a squared would be a non-negative number, but also we see that 2 times something is equal to a squared. So that is, you are exactly right. But the point I'm trying to make here, I know I was really vague, but it's worth a try. So the idea is that 2 times a number is a squared, so that means that a squared, or 2, divides a squared. So by definition, 2 divides a squared, which means that a squared is even. All right. Now, as a reminder, we showed that if 2 divides a times b, 2 divides a or 2 divides b. So if I put that into context here, remember that a squared is just a times a. So what we have using our lemma is that 2 divides a times a, therefore 2 divides a or 2 divides a. So if 2 divides a or 2 divides a, that means that 2 divides a. Which means that a is even. Does that make sense to everybody? Any questions in there? Oh, I did get an A is even in Discord. Cool, thank you. All right. So we have A is even. What that means now is if I can take this, I'm going to actually start over with this and say, okay, well, if A is even, it's equal to 2 times some integer, let's say k. So if I look at this portion here, I had 2b squared is equal to a squared, so 2b squared is equal to a squared, but then 2b squared is 2k squared, so 2b squared is 4k squared by squaring both of these terms. And now I can divide by 2 and I get b squared is 2k squared. Well, what in the world does that mean? Well, that means that 2 divides b squared. But for the same reason, that means that 2 divides b. So a is even and b is even. So what have we just said is that if the square root of 2 was rational, that is, it would have to be equal to an a over b, where either a is odd or b is odd. But it also have to be the case that both a is even and b is even. So if both of these have to be even, but both of them can't be even, what does that mean? Well, that means it's a contradiction because we're saying that something that can't be true. It both has to be true and false at the same time. So therefore, the square root of 2 cannot be rational because it leads to the contradiction where both a and b are even and either a or b is odd. Therefore, this cannot be rational. Therefore, this has to be irrational, or we get our original statement that the square root of 2 is not rational. All right. If you guys have any questions in there, feel free to ask. Otherwise, what I want to point out is the big thing here is that we've talked about rational, we've talked about irrational numbers, but up until this point, we haven't actually shown that there were any irrational numbers. We've mentioned that we think some are irrational, but we haven't actually given a proof that any number is irrational or any number is not in the set of rational numbers. So this is the first number that we've actually shown this cannot be rational. So therefore, there has to be numbers other than rational numbers. So we can't write every number as a fraction of integers. And since we have an example now where we've given a proof, we know that has to be true. As a point here, a little bit of history is the basic tenet of the Pythagorean religion was that all is number, and they believed that every number could be written as a fraction of integers or written as a ratio of integers. And they actually worked with a different number as 1 plus the square root of 5 over 2, but they were able to prove that this was irrational, or it was not rational. So their core belief that every number was rational, they were able to disprove. And I think it's the only time ever that a religion has disproven its own basic tenet. So I thought that's a very neat story. Take it for what you will, but there you go. All right. Any other questions on there before I move on? All right. Other than the square root of 2 being irrational, the other major proof that people do by contradiction is that there are infinitely many primes. And this problem actually goes back, and this proof in particular goes way back to Euclid and the elements. So that's over 2,000 years ago. Euclid wrote up his book, about geometry and all this other stuff, but in particular he included a proof that there were infinitely many prime natural numbers, and that is exactly the proof we're going to be doing today in class. I just like to think about that because I don't really know any other course of study where we're learning the exact same thing we learned 2,000 years ago. That other than notational changes, there's been no changes to this proof in over 2,000 years, and it's still valid, it still holds true, and that's just pretty amazing to me. The fact that once you've proven something, it's true forever. And I guess 2,000 years isn't forever, but it's a very long time. In the sciences or other things, someone would have come along with, oh, there's a better way to look at this, but nope, it's still exactly the same as it was over 2,000 years ago. So just some food for thought there. I just find that interesting. So how are we going to prove that there are infinitely many primes? I do want to point out that if we wanted to show that there were infinitely many primes directly, we'd have to construct infinitely many primes. We'd actually have to say what they all are. So what would a proof like that look like is, well, what are the prime numbers? Well, if we start with the prime natural numbers, the first one would be 2, then 3, then 5, then 7, and then 11 and 13, and I'd have to go on forever to show that there are infinitely many of them. As a point, we've proven that there are infinitely many primes over 2,000 years ago, but to this day we still haven't actually shown a constructive argument that there are infinitely many primes. One of the big things about the Riemann hypothesis, which was one of the millennial problems, was that if you use the Riemann hypothesis, you could figure out where these primes are going to be, and you can actually show that you can then construct infinitely many primes using this idea. And so this was a huge was a huge open problem in mathematics. I think last year or 2 years ago, there's a mathematician who came out with what he said was a proof, and we don't really know if it's a proof or not yet. I haven't seen it, but it is published out there, and people are looking at it trying to determine if all of the ideas are correct or not. And so it takes time to kind of verify proofs. And at some point we'll get either yes or no. I haven't been able to find it. I'm sure it's out there somewhere, but there you go. So either it is still an open question, or it's taken over 2,000 years and we're just finally finding a solution to show that there are infinitely many primes directly. So I just want to point out that's the difference in difficulty between these two proofs. It is much easier to do a proof by contradiction, so we're going to assume there are finitely many primes. So the negation of there are infinitely many primes or there are finitely many primes, and I want to see that this leads to a contradiction. How am I going to do that? Well, the first thing I need to note is that if there are finitely many primes, I can actually list out all the primes. So this is P1 through Pk, and I can list these all out. There are all the prime numbers. I don't actually know how many there are, but there's, for some integer k, there's a finite number, so I could potentially list these all out. So there's all the primes. Now what I want to point out here is if I have some other number, let's say a, that is not an element of P, then if A is not prime, that means that there is a divisor other than 1 in itself. So A can be written as, let's say, A1, A2. But if this is prime, then I have that A is divisible by a prime. But if they're both not prime, then I can rewrite them as, let's say, A3, A4, A5, A6, where each of these are smaller than these. So if any of these are prime, well, then we have that A is divisible by a prime. But if not, I can continue on, where each time I continue on, each of these is going to be smaller than the one before. So if each time I divide, I get a smaller one than the ones before, by the same argument as I had for my dividing by 2 thing, I'm eventually going to have to run out of natural numbers. All of these have to be bigger than or equal to 2. So if I keep getting smaller and smaller, however big this is, eventually I'm going to be smaller than 2 if I can divide forever. So what does that mean? Is that if A is not in P, then there exists a P sub I in P, or some prime number, such that P sub I divides A. Because if I were to get to a prime, I can't factor anymore. So if I don't ever get to primes, I keep factoring forever. So I get a contradiction. So if I start with A, I have to be able to factor out until I get some prime is going to divide A. Does that argument make sense to everybody? I want to make sure you see what I'm saying there before moving on. All right. So if any number has to be divisible by one of these, if I can show that there is some number that is not divisible by any of these, and then I have a contradiction. So I have to find a number which is not divisible by any of these things. Well, how would I find such a number is, well, what I want to talk about here is notice that each of these are greater than or equal to 2. And what we know is that we'll say n divides A if and only if A is congruent to 0 mod n. So I'm going to use modular arithmetic again, and I'm going to remind us that A is congruent to B if and only if n divides B minus A. So a consequence of that is that n divides A if and only if A is congruent to 0 mod n. So that is, if I divide by n and get a remainder of 0, then A has a remainder of 0, therefore n is divisible by A. And if n divides A, or if n divides A, then clearly the remainder is 0, so A is congruent to 0 mod n. And that's the only way that n can divide A. And as long as n is greater than or equal to 2, then 0 is not congruent to 1 mod n. There you go. So if we took mod 1, I guess 0 would be equal to 1. But mod 2, mod 3, anything else, if I divide by 2 and I have a remainder of 1, that is not a remainder of 0. If I divide by 3 and I have a remainder of 1, that is not the same as a remainder of 0. So, since these are all prime, they're all bigger than or equal to 2. So what I can do is, kind of an outline here, is if I can find an A that's congruent to 1 mod each of these numbers, then it cannot be divisible by any of these numbers. Therefore, we can find a number that is not divisible by any of these. All right. There's my goal. How do I find a number that's congruent to 1 mod every one of these? Well, notice that if I want to find a number that's congruent to 1 mod p sub 1, I could just take p sub 1 plus 1. If I wanted to find one that's congruent to 1 p sub 2, I could take p sub 2 plus 1. And in general, I could say p sub 1 times n plus 1 is congruent to 1 mod p sub 1, because this is congruent to 0. So if I take p sub 1 p sub 2 plus 1, notice that this number is congruent to 0 plus 1 mod p sub 1 or p sub 2. Because if I take mod p sub 2, this is 0, and I'm left with 1. If I would take mod p sub 1, this is 0, and I'm left with 1. So if I wanted something that was congruent to 1 mod both p sub 1 and p sub 2, I could multiply these together, add 1, and so therefore this number cannot be divisible by p sub 1 or p sub 2. Well, since I want it true for all of the p sub k's, or p sub i's, let's just take p1 times p2, p3, all the way up to p sub k and multiply those all together. This number is indeed divisible by every one of these prime numbers, so let's just add 1. And then what I get is a is congruent to, well, 0 plus 1 mod p sub I for each p sub I. Therefore, p sub I does not divide a for all p sub I. So what that means is that if there were finitely many primes, I could multiply them all together and add 1. This new number would not be divisible by any of the primes, and therefore, in and of itself, would actually have to be prime. But since these are all of the primes, we can't have another prime. So we get that if there were finitely many, we can't actually find we would have to always be able to add in a new one. So that contradicts the fact that these are all of those. Hence, we have a contradiction. Therefore, there cannot be finitely many primes, and there have to be infinitely many primes. So that's our proof that there are infinitely many primes as per Euclid. Any questions on that one? All right. I don't see any questions. You guys are being quiet today, which I did get some responses though, so thank you for that. There's nothing wrong with that. I just wanted to let you guys know that those were some major proofs. The square root of 2 one, there's actually other ones in the homework like that you would do. I wouldn't necessarily ask you to show that there are infinitely many primes on a test. But now that we've done it together, I could ask you, show that the square root of 3 is irrational, or the cube root of 2 is irrational. And some of those are on the homework on this chapter, so I would suggest looking at those. And so there are a few problems, and that will be due on Tuesday, so please look over the proof by contradiction chapter, so that if you have questions, we can do that. I know we still have plenty of time left in class, but I feel like we've done a lot today, and we've gone over some interesting proofs, and I don't really want to push too hard since we're online learning instead of in class. So I'm going to let you guys go there, and I will see you on Tuesday. Thank you very much for coming.